So we are looking at linear classification, and I'll quickly remind you of the properties of hyperplanes that we wrote down in the last class. Okay, we will denote by f of x. Right, so the hyperplane is essentially given by solving f of x equal to 0. Okay. Well, what I really want is okay. Right. So I don't care about the other properties. What I really want is for you to recall that the signed distance to the hyperplane is given by f of x, right? Okay. So then we looked at the perceptron learning algorithm. So what was the problem with the perceptron learning algorithm? Convergence, yeah. So if it is well linearly separable, it will converge, but it might converge slowly. If it is not linearly separable, it will cycle, okay. But if it is linearly separable, what can you say about the convergence apart from the fact it's slow? It depends on the starting point, right? It's not definite as to where it will actually converge, right? There is no particular solution to which it will converge, right? So now what we are going to try and do is try to characterize a specific optimal solution, right? We will first start by considering the case of linearly separable data. So just like whatever I have drawn here, so data points given to you is actually perfectly separable by a hyperplane, okay, right. So we will start with this case. Now I am going to try and characterize what I mean by an optimal separating hyperplane. Okay, give me some options for what could be optimal. Think.
The distance is sum of modular sum of distances is maximum between the points and the separating hyperplane.
The modulo sum of the distance of all the data points to the separating hyperplane?
Yeah, because like if the line is slanted, then maybe the closest point is farthest away.
Exactly, right. So that makes a lot of sense. So that's exactly what we are going to use, right. So we are going to maximize distance of closest point to the hyperplane. Right. So essentially, so if you think of this data, right, so that is close, but this is closer, right. So if I want to maximize the distance of the closest point, what should I do? Move it like that or like that, whatever, somewhere, move it farther away from this, right? So what, how much farther away can I move it? Until other side also, say the closest point from both sides should be at the same distance, right? So on both classes, right, the closest point should be at the same distance from the hyperplane, right? And I have to choose an appropriate orientation for the hyperplane so that this distance is maximized, okay? So that's essentially what we are going to try and do. So since of erasing the hyperplane, drawing it again, I just moved the data point so that this is closer now, right? Right. So now I'm essentially going to have a slab in some sense around the separating hyperplane, which will have no points, right? So on the thickness of the slab will be the same on either side of the hyperplane. So that's essentially what I am looking for. So this is called the margin, okay? Whatever you cleaned up around the hyperplane is called the margin, okay? So that's why these kinds of optimal hyperplane classifiers are sometimes known as max margin classifiers, right? Because you are trying to maximize the margin, right? So distance of the closest point to the hyperplane is the margin. So in fact, so the margin would be that, okay? So we know what xi transpose beta plus beta naught is. That's the distance, signed distance from the hyperplane. So I multiply by yi so that I always get it positive, right? Right. So essentially what I am saying is, I look at the quantity, this is essentially the distance a data point is away from the hyperplane, right? I am saying that every data point has to be at least m away from the hyperplane. That is my constraint, right? So I go through all my training data points 1 to n, and I am saying that every data point should be at least a distance m away from the hyperplane, and under that condition maximize m, right? So I can't make m arbitrarily large because I might not be able to find a beta which will satisfy for every data point, okay? So this is how I will write down the optimization function. What we wanted was maximize the distance of the closest point to the hyperplane. So now what I am going to say, every point should be at least m away. Now maximize m, right? This will automatically maximize the distance of the closest point, right? So what do you think will be the distance of the closest point? Whatever m you end up with, right? So whatever is optimal m for this will be the distance of the closest point, and that will be the margin. So that is why essentially what you are doing is you are directly maximizing the margin, okay? So we have this constraint that norm beta should be 1, right? Because we don't want the solution to blow up arbitrarily. So instead of that, right, we will get rid of that by right? If I didn't have the constraint of norm beta equal to 1, I can arbitrarily make beta large here, right, and make things larger than m, right? So now I am normalizing by beta, right, so that I do not have to worry about that. I can remove this constraint here, right. Instead of that I put the norm beta here in the denominator in the constraint, right. Does it make sense? Right. But then I can do something more interesting now. Can I do that? Right? Great. Now let us step back and think about it for a minute. So if something satisfies this constraint, right, I can arbitrarily scale it, right, that will still satisfy the constraint. If you think about it, because I have norm beta on this side, so if a beta already satisfies this constraint, okay, I can just scale the beta, okay, and then that will satisfy the constraint as well, correct? So I can arbitrarily set right. I still have to find out the direction of orientation of the beta. I am just saying that whatever orientation of the beta you pick, you normalize it so that the norm of beta is 1 by m. Okay. So now what happens if I set that? Okay. So people with me so far? Right. So kind of I started with this constraint, started with that optimization problem, made the assumption that well norm beta is 1 by m, right, and I came up with this problem, right. So I have done nothing, just little algebraic manipulations. In fact it's geometric as well, I am just not drawing the geometry here, right. But then the objective function also now can change instead of maximizing m, I can minimize norm beta because norm beta is 1 by m, right. So I can do that subject to the constraints here, right. I am going to do all of that so that it makes it easy for me to take derivatives, minimize and things like that, right. So I just made it a squared function so that I can manipulate it more easily. It does not matter, minimizing norm beta is the same as minimizing beta squared, right. So norms are anyway positive, non-negative, yeah. So is it clear so far? Right. So essentially now I can go and say that this margin is actually going to be what? Right. So another way of thinking about it is, what I am trying to find is a minimum norm solution such that all the data points are what? Are correctly classified, right. So what does this mean? I mean yi xi transpose beta plus beta naught is greater than or equal to 1. That essentially means that xi is in the right side of the hyperplane, right. You remember that? So yi is plus 1, then this is also positive, right. Then I mean it has to be at least plus 1, right. So not only should this be positive, this has to be at least plus 1, right. Then you will get a 1 here. And similarly if yi is minus 1, which is the other side of the hyperplane, so this term has to be at least minus 1, right, so that you will get a plus 1, right. It will be greater than or equal to plus 1. So you know that all of the data points are correctly classified, correct, and minimizing beta essentially is the smallest possible beta, right. So, finding the smallest possible beta such that data points are correctly classified, and not only correctly classified, they are at least a certain distance away from the hyperplane.